Okay, there you go.
Okay, so it's a pleasure to welcome my good friend Adrian Feiguin. Adrian got his PhD in Rosario, and then he went to Tallahassee to the National High Magnetic Field Lab in 1999, where we met. We both worked at the Elvio Dagoto's group. He stayed there until 2001. Then he went to Irvine to work with Steve White, the inventor of the MRG method. He stayed there until 2005. Then he moved to Station Q in Santa Barbara. It's a lab that was set up by Microsoft, and he stayed there from 2006 to 2009. 2009, he got a position in Wyoming, at Wyoming University, or University of Wyoming, I think, yeah, University of Wyoming in Laramie. He stayed there until 2012, and since 2012, he has been in Northeastern University in Boston, where he's now tenured as an associate professor. So today he's going to talk to us about spectral functions using neural networks. So thank you very much, Adrian, for accepting the invitation. The microphone is yours.
All right. Thank you, George, for a very kind invitation and for the nice presentation. The pleasure is really mine. It's always nice to discuss physics with you guys. And it's let's I want maybe I shouldn't be apologizing for being Argentinian today, but I feel like I'm very embarrassed for my president's words, and no way to defend him.
We forgive you. We forgive you.
Just, when I heard the news, I was like, "Come on! I'm giving a talk in Brazil tomorrow, and I cannot show my face now." But anyway, all right. You should only know that I don't share his confusion. Let's put it that way, kindly. All right. So today I'm going to talk about spectral functions using neural networks, and this is some recent work that we've been doing with my two students, Doug Henry on the left, and Hongwei Chen, and also my postdoc Phil Weinberg collaborated in this project. And some of the results that I'm going to present have been published already in this PRB a couple of years ago, and the new results are on the archive and were recently posted. So before I get into the neural network business, I want to give you some motivation. We all know that the Manybody problem is complicated, but for those in the audience that are not familiar with it, and I hope I'm not underestimating my audience, I want to give you a brief overview, at least the intuitive picture. So here what I'm going to do is compare the single particle problem to the Manybody problem and give you an idea of why the Manybody problem is so complicated. So when we study solid state and we learn nearly free or tie binding from Ashcroft and Reming, we basically solve a single particle problem, right? So what we do is we have a bunch of orbitals describing our here I put 4 orbitals along a chain. This is not a square lattice. This is a one-dimensional arrangement of orbitals. And here what I'm showing is 4 possible configurations of one particle in 4 orbitals with spin, right? So this particle can be, where's my cursor? It can be here, 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 right? So now I can also a particle spin down, and I'll have 4 other configurations for the spin down. But these are all single particle states, and the problem can be solved exactly very easily because it's basically a 4x4 matrix. Now, if you want to add more electrons to your system, what we do in the case of non-interacting particles is we just populate our states following Pauli's rules, right? So basically, we're gonna have, let's assume we have some confining potential and we have these discrete energy levels. And this is kind of like the hydrogen atom, right? We solve the hydrogen atom for a single particle, and then we start populating the orbitals of the hydrogen atom. We put a particle spin up, and then we put one spin down. We basically now this shell is full. We cannot put any other electrons, so we move up in energy, and we start putting 2 electrons on each energy level until we reach the chemical potential. So this is a product, what we call a product state, because it's basically a problem of a single particle, and there's no entanglement. The particles don't talk to each other, and they don't see each other, and basically we can get away with it by solving a simple matrix, and we can go to very large system sizes because of that. But now let's see how that is not the case when we have many-body interactions. When we have many-body interactions, we have to account for all, now we have, imagine, 2 electrons, one with spin up, one with spin down. We have to account for all the possible configurations of 2 electrons. We cannot simply work with the single particle basis anymore. We have to account for the fact that maybe 2 particles, when they are occupying the same orbital, feel an interaction, and or maybe when they're sitting farther apart, they feel a long-range interaction, and we cannot describe interactions in a single particle basis. So now the number of configurations of 2 electrons in 4 orbitals is 16 instead of 8 as before. And now we have to solve a 16 by 16 matrix. And one can easily convince oneself that this number of configurations grows very rapidly with the number of particles or with the system size. Now, these particles are going to describe a state that is entangled, and it cannot be written as a product state. So the behavior of each electron is dictated by the behavior of the other electrons, and we cannot separate the degrees of freedom. And in a nutshell, the many-body problem consists of solving the Schrödinger equation, right, in this many-body particle basis. So we have a Hamiltonian that contains all the interaction terms. We have a basis of states, and all we have to do is solve this eigenvalue problem, and we can do it easily if we could write the Hamiltonian and all the matrix terms by calculating these matrix elements and plugging this equation into an eigenvalue solver and get all the eigenvalues and eigenvectors, and we know all the physics about your problem. But again, this is easily said, but it's not easily done, because the number of configurations grows very rapidly with the number of electrons or with the system size, and this number rapidly exceeds the memory of the largest supercomputer in the world. So this leads us to, well, here are some examples of what can be done. I'm sure these numbers are outdated, but for the Hubbard model, for instance, with 20 sites, we can solve, for instance, the case with 10 electrons up, 10 electrons down. The dimension of the Hilbert space is huge, it's 2.4 times 10 to the 10. But after symmetries, this can be reduced to 100 million states. So imagine you have to analyze a matrix that is 100 million by 100 million. So the number of matrix elements is 10 to the 16. But there are some tricks that allow you to reduce this number by using symmetries and analyzing the matrices in blocks. Well, similar numbers appear for the TJ model. This is the largest system size, 32 sites. The Heisenberg model on the square lattice, 36 sites, 6 by 6. And some cases with extra constraints, one can go to larger system sizes, for instance, for ring exchange models and things like that. But this gives you a flavor of the order of magnitude and the complexity of the problem, and why in basically 30 years since I started my physics career, we could, this number hasn't changed. So so this leads us to what we call the representation problem, right? So we have this state. This is a Manybody state, and we write like this. So this is the sum of all possible configurations that I label by some local degree of freedom. For instance, could be spin, up or down, could be occupancy, could be an empty orbital, an orbital with 2 electrons, an orbital with 1 electron up or 1 electron down, and the wave function will have a coefficient, which is going to be an amplitude, what we call the amplitude for each spin configuration, for each configuration S, and of course the probability of seeing that particular configuration is the square of the amplitude. So again, the number of configurations or coefficients in this wave function grows exponentially, and it cannot be stored in larger supercomputers. So this is the representation problem. So how can we get around it? I mean, obviously not by brute force. We have to do it with ingenuity. And the idea would be to basically reduce the number of free variational parameters that we need to calculate. So suppose that we can propose a functional form for this psi. So this psi now is a function of the configuration, and maybe it's a simple function. Maybe it's a function depending on only on m free parameters. And in that case, this psi will be a function of these m parameters alpha, and this will be a function that for each value of alpha will give me a different wave function, right? And the idea would be now to basically find the best alphas, or the best set of parameters alpha that approximate the actual exact wave function that I'm looking for. By the way, feel free to interrupt me at any time in case I'm not being clear or you have any questions. One example of a very accurate ansatz, or a very accurate guess for a wave function, is given by matrix product states. This is basically the structure of the wave function that you obtain when you use the density matrix normalization group method, and it's very accurate for one-dimensional systems that are relatively weakly entangled. So the idea is that each coefficient now, psi, you see, is this big expression. This big expression is basically a product of matrices. In this particular case, the first one is going to be a vector, and the last one is going to be a vector because I'm using open boundary conditions in this case. Each matrix will depend on the index S, also the spin configuration, whether the local degree of freedom is, spin up or spin down, or empty or occupied, double occupied. And it's going to have one index if it's a vector, 2 indices if it's a matrix. So this is basically a D by D matrix, and I can change the value of this dimension D, and this will give me the number of free parameters. Basically, the free parameters are the matrix elements of this D by D matrix M. And then all I have to do to obtain the coefficient psi of alpha is trace over all these alphas, right? And I'm going to get a number. And in short, it looks like the notation looks like this. So this is my coefficient now. And it turns out that it's a very accurate ansatz, but it works very well in one dimension. But it's very hard to generalize to higher dimensions. So there are some ideas floating around, or you may have heard about tensor network states, PEPs, Mera, and other ideas. But in this particular case, what makes it very nice is that these coefficients or these matrices can be optimized very efficiently using simple algebra. So you only need to use some algebra, and you can do a very efficient optimization of the parameters without having to do sampling, as I'm going to show next. So the challenge is actually to go to higher dimensions, and that's why in the past couple of years we have heard a lot about neural networks. So I'm going to give you an overview in a minute. But first, I want to introduce the problem that I'm going to use as a test, like a for showing all the results. So this is going to be basically the Heisenberg model for spins. So I'm going to assume that the only degrees of freedom are localized spins up or down. So basically any spin, any configuration S that was generically referring to before as S1, S2, S3, SL, is going to be now each S is going to be either as an arrow pointing up or an arrow pointing down. And as you can see here, I'm going to have 2 to the L configurations. So this can be up or down, that's 2. This can be up or down, that's 2 times 2, 4 times 2, 8, and so on and so forth. So you can see how rapidly this number grows as we increase the number of spins. So the problem, so this is the basis, and now the problem is defined by the Hamiltonian, and the Hamiltonian contains all the interactions between the spins. These are spin operators acting on side I and side j, and this is the sum over all neighboring sides on the lattice. And there is a prefactor j, j1, and there is also a sum over second neighbors that I call with this double bracket ij with a j2. So in one dimension, this looks like this. So I have my chain with j1, that's the zigzag dashed line, and then I have the j2 between every other spin on the chain. On the square lattice, the J1, J2 looks like this. You know, I have a square grid where I have one spin at each vertex of the grid, and then along the diagonals, I have a J2. This talk is mostly about methods. I'm not going to talk too much about physics. So it might become a little, you know, I started slowly, but it might become a little technical in a minute. So I'm not going to talk too much about the physics of this problem. And the reason why we are interested in this Hamiltonian is because not only is a paradigmatic problem, a paradigmatic Hamiltonian that includes what's called magnetic frustration, it also may realize spin liquid phases and some exotic states of matter. And that's why it's attracted a lot of attention in the past more than 25 years. And actually, I worked on this Hamiltonian in my PhD thesis. People are, you know, we're still working on it. As simple as it looks. So one way to parameterize a wave function, besides the matrix state wave function that I showed you earlier for spins now, is the Jastrow wave function. And in the Jastrow wave function, we have each coefficient psi as the expectation value of this operator. This operator is basically the exponential of this sum. This is the sum over all pairs of spins, ij, szy, sgj, so the operator sz. Basically, this is a diagonal operator that is 1/2 if the spin is pointing up, and minus 1/2 if it's pointing down. So it's a number when you apply it to a configuration with some prefactors alpha ij, and these alpha ij's are our free parameters that we want to optimize. Since this operator is diagonal, given the spins S, it directly gives you a factor. It's called the Jastrow factor, right? So it's just a number. So given a spin configuration, we already know the coefficient. It's very easy to calculate, straightforward. That's it. So this wave function, where does it come from? Well, it comes from some physical intuition. More precisely, comes from spin wave theory. So it's a mean, in a sense, it's a mean field solution. And it breaks SU2 symmetry. So it basically starts from the assumption that your ground state has order, has magnetic order. And if you have magnetic order, that means that you cannot accurately describe disorder phases like spin liquids. But you know, it's a good starting point. It's very simple. We can play with it. And people have used it a lot to study the simple Heisenberg model without the J2. And it can be simplified even further if we assume a functional form for this alpha ij. So if you assume that this alpha ij depends on the distance between the spins only, you can propose a parametrization like the one shown here, in which you have only now a single pre-parameter alpha divided by the distance. So you're assuming basically that the coefficients decay algebraically with the distance. You can also, I mean, make it more complicated and maybe add the power here, distance square or something like that, or distance to some other variational parameter, and then you have two variational parameters. You can tweak it and make it as general as possible. Here in this figure, I'm showing you, for instance, a result from Sorella's PRL in 2005, in which he showed how you can improve the algorithms to optimize these wave functions. And here you see how basically these coefficients depend on distance. So this is distance. This shows how this is for 300 sites. This is how as you optimize the wave function, the coefficients evolve eventually to something that looks kind of algebraic. And the cost of optimizing these wave functions and the method we use to optimize these wave functions are crucial here, and I'm going to tell you a little more next. But before we get there, I want to tell you a little bit about why we are talking about machine learning, among other things. And well, in this context, machine learning is nothing else but the fact that we're using neural networks as a representation for these variational wave functions. So in particular, I'm just showing you one kind of neural network. It's called a restricted Boltzmann machine. In the literature, you're going to find many. Actually, in our group now, we are using convolutional neural networks. We're using variational autoencoders, other wave functions. But this is the simplest one, and the one that started this craze about machine learning. And this was proposed by Giuseppe Carleo and Matthias Streuer in a Science article in 2017. So as you can see, this is very recent, but the number of papers, probably this paper has more citations than all my papers cited together. But in any case, this has started a sort of revolution, if you will, in computational physics, because now we have a way to use the technology of machine learning that has been developed over the past 20 years by companies such as IBM and Google and Amazon to now solve the Manybody problem, right? So this machinery basically gives us the infrastructure that we need to now tackle this complicated problem. The idea behind the restricted Boltzmann machine is very straightforward. So this is a simple neural network, has two layers only, something that's called the visible layer, where I put all my physical degree of freedom. Here I labeled them as sigma instead of S. I apologize for the change of notation, but this sigma is actually the S here, right? They are in the previous slides. And then there's a second layer. It's called the hidden layer that has auxiliary spins, if you will, called H. And they also have two possible orientations, up or down, or they can assume two values, plus, minus 1. And they're all connected to each other in between layers through some weights, these weights ij, right? This W. So this is W11, then we have W12, 13, 14, and so on. 21, 22, 23. So we have, it's a large number of weights. It's basically n square weights, if you will. And then we have some biases, A and B. The A's act on the physical spins and the B act on the hidden spins. And now the wave function looks like this. The coefficient now will depend on the weights AB and the biases, sorry, AB and the weights W, as the trace or the sum over all the hidden variables of this exponential. Basically, it's like a Boltzmann factor, e to the minus some energy. And it's a classical energy that depends on S and H. Now you see that once we sum over all the H's, the result will only depend on S. Right? Will give us a number, the same as before. For this energy, this classical energy, we pick something that looks like an Ising model, right? It's a generalized Ising model. So we have double sum. This is kind of like a spin glass, if you will, but with Ising spins. Sum over all spin configurations, all sides, I mean, Ij, Wij, S on side, the spin Si, and the hidden spin Hj. And we have the biases that are basically magnetic fields acting on the physical spins and the hidden spins. It's a very simple Hamiltonian. It's classical Hamiltonian. And this can be, since we're tracing over the H's, it turns out that this trace can be done exactly, this sum. This sum gives rise to this cosh, this cosh factor. It's a hyperbolic cosine, right? And you see that basically this argument or phase in the cosh depends on these W's and the spins. The sum over all the spins, Wij, Si. Basically, when you sum over the hidden variables H, you sum over a possible exponential and a negative exponential with the same argument, and you get the hyperbolic cosine, right? Now, this is something that people have used in machine learning to represent probability distributions. And here we're going to use it to represent, well, basically a wave function, which is also, in a sense, a probability distribution. Now, the difference is that now we're doing quantum mechanics, right? And in quantum mechanics, your coefficients can be complex. So we have to generalize all this machinery to account for the fact that all these coefficients, W and A and B, have real and imaginary part. And this can be the cosh of something that is complex. And this new wave function, in a sense, it's more flexible and has, as I'm going to show next, more expressivity than the Jastrow wave function. And the reason is that these coshes here, if you expand them in terms of the spins S, will have terms that are SS, SSS, SSSS, and multiple powers of S, right? So basically, we have all powers of S. If you expand an exponential, you get all powers of S, and now you're basically accounting for not only two-body interactions like the Jastrow wave function, but you count for many body interactions at all orders, in a sense, and distances. Any questions? Maybe this is a good time to stop for a sec and answer some questions. No questions?
I have a question yeah. Quickly. The number of elements in the hidden layer is the same as in, you are representing there a different number, so there is no...
It can be larger.
It can be larger.
Ideally, it's larger.
It looks like a bath, right?
It looks like a bath, and you can increase the size of this hidden layer as much as you want. It will give you more flexibility. It turns out that you can improve what I'm going to refer to next, the expressivity of the wave function, but up to a certain point. You keep increasing it and nothing changes, and you only make the problem more complicated because you have to optimize more parameters. But it turns out that there is some evidence that even if you overshoot and you make it too large, conversions might become easier. This is another story, but in general, we pick, for all the cases I'm going to describe next, the hidden layer to be 3 times larger than the visible layer.
For a moment, it even looks like you are making the problem more complicated than originally, right? When you add all these connections and all the path and everything, but I know that the idea is not that. The idea is to solve the problem, but it looks like you made it more complicated.
It looks more complicated because you have more spins, if you will. But as I told you here before,
you trace everything.
You're tracing over the edges, and this trace can be done exactly.
Okay.
So you see that in this expression here, the h degrees of freedom disappear completely, and you only have a mathematical expression for the sigmas. So you can completely forget about the picture I'm showing here. Okay. And if I give you an expression like this, you say, okay, this is a variational wave function. I need to optimize the w's and the a's and the b's, and that's it. Okay. But it has some mathematical structure that originates from this picture, basically.
Okay, thank you.
So
sure.
I have a question. So how sensitive is this of the convergence regarding this decision? Can I say decision function? This cosine, hyperbolic cosine.
It's it depends on the problem. It depends a lot on the problem. So, but typically optimizing this wave function is not that difficult. It's very difficult in the cases I'm going to show you for the ground state at least. It's very difficult, except when you go to system sizes. So, for instance, a student of mine now is studying systems like 12 by 12. And when you do square lattices with 12 by 12 spins, it becomes quite challenging. Now you can think, okay, I can do quantum Monte Carlo for 40 by 40. Why I need to do 12 by 12? But you cannot do quantum Monte Carlo for when you have frustration, for instance. And another thing is that yeah, well, basically, this 12 by 12 is still beyond what you can do with tensor networks or DMRG accurately. So, in most cases, so.
And quantum Monte Carlo has a problem with low temperatures, right?
Quantum Monte Carlo, it depends on what Monte Carlo, because you can do projector Monte Carlo and you're working at 0 temperature. So
okay.
Depends on your
flavor.
Flavors of quantum Monte Carlo, exactly.
Okay.
All right, so this brings me to precisely answering Edson's question, to the issue of representability. So what kind of wave functions can I represent with this mathematical structure, right? Because you may say, okay, now I can represent any wave function in my Hilbert space, but that's not quite true. I'm putting some physics by hand somehow, and this means that I can only represent certain manifold of variational states that live in this bubble that corresponds to all the possible values of alpha, right? And so my Hilbert space in reality is much larger than this, and then the set of variational states I can represent with my wave function is just a subset of the total Hilbert space, and it's not. Well, and this will depend on which formulation I use. If I use matrix plus states, it will be different, right? So in reality, the picture is more or less like the one shown here, where these variational states sort of percolate all over the Hilbert space. And in principle, you can think that you can get as close as you want to a physical state if you only increase the number of variational coefficients or you the number of hidden variables, for instance. But that's not always the true, right? So, for instance, in the matrix plus states, we know that all matrix plus states have correlations that decay algebraically. So the was it algebraically or exponentially? I forget. Jeez. Anyway, so by so this means that in a sense you can define for a wave function its expressivity. You know, it's how close you can get to an actual many-body state that you are seeking. And some wave functions have limited expressivity. For instance, the Jastrow wave function, and some wave functions are way more expressive, if you will, like matrix states or RBMs. So now, when we say that we need to optimize these variational parameters, what do we refer to? So we refer to trying to approximate a target function, right? So a target state. So we have our physical state, and we have our variational state, and we want our variational state to be as close as possible to our physical state. How do we do that? Well, one way is, for instance, if you're interested in the ground state, you just minimize the energy, right? So you minimize the variational energy, you define your energy as the sandwich of the Hamiltonian with this wave function, and we want to find the alphas that make this value as low as possible. So basically, it's you want to find the minimum of this function that is defined in a manifold that is multidimensional, parameterized by these alphas. And it turns out that for this particular case, and actually for any observable, you can re-express it after some manipulation that I skipped here because I don't want to get too technical with equations. Your energy can be interpreted as the sum over all spin configurations of the probability of finding that configuration times some local energy that we call corresponding to that configuration. And I forgot to put the expression for the local energy. The local energy is basically the sandwich of the Hamiltonian with the spin configuration. And the probability is basically shown here, is basically the coefficient of the wave function squared normalized by the sum over all the configurations. So clearly this probability is well defined, is positive because it's squared and it's normalized to 1. This looks a lot like, you know, if you took StatMac, you know that this looks a lot like Boltzmann, for instance, average, if you will, a thermal average, where P is now your Boltzmann factor. So basically, what we're doing here is we're replacing our Boltzmann factor by the probability amplitude of finding that particular configuration. And so, how do we calculate this energy then? We still have an exponentially large number of spin configurations, right? So how do we carry out this sum? That's impossible. So what we do is we do quantum Monte Carlo, right? So we do stochastic sampling over spin configurations, and it's similar to doing classical Monte Carlo for the Ising model. But now, instead of using the Boltzmann factor, we use the coefficient square of the wave function. And this is what we call as variational Monte Carlo, basically. And so with this, I'm just telling you, okay, to calculate these quantities or these averages, we need to do stochastic sampling, and it's a quite costly computation, but can be actually carried out quite efficiently, especially if you have a cluster and you can parallelize it. So now what we need to do, and this is probably the heaviest slide in my presentation, is to approximate, for instance, the ground state. And so instead of doing this variational minimization, so this variational minimization here can be done in many ways. And one way to do it is by using gradient descent, for instance. You know, you calculate some energy for some alphas, and you calculate the derivatives with respect to alpha, and you evaluate the derivatives, and you move in the direction opposite to the gradient. This is what's called gradient descent, right? But you know, we know after 20 years of machine learning that this is not the optimal way to do it. There's a much better way to do it, which is called the natural gradient descent. And I don't know if I need to spend time in this slide too much, but it's actually crucial to describe the methods that we developed. And the idea is to, in reality, to evolve our wave function in imaginary time. So if we have a wave function that has some overlap with the ground state, we can evolve it with this sort of modified Schrödinger equation, in which instead of time, we have imaginary time. You see there there's no complex unit here. The I disappeared. And this is like evolving in temperature, like starting from high temperature and going to low temperature. And what we need to do is basically minimize the projection error between this function that we're seeking, in this case, the derivative of the wave function and the target wave function. And this gives you a set of equations. So basically what we are doing in reality is we are moving in the variational space of the variational wave functions in a way that will approximate the actual target wave function as close as possible, moving in the direction of the target wave function. So this is different than natural gradient descent. So sorry, than usual gradient descent, because gradient descent moves in the Euclidean geometry of the parameter space. So you use the derivatives with respect to the alpha parameters. And natural gradient descent uses the information geometry of the variational manifold, and basically consists of minimizing this angle between the two functions, the target function phi and the function psi that you're using to approximate it. So imagine this is your ground state, and this is your variational wave function, and what you want to do is minimize the angle between the two and make them as parallel as possible. And we don't care about the normalization because, you know, in quantum mechanics, the normalization is not important, right? It's just a number. And the importance is the angle. What's important is the angle. And this gives rise to a different kind of metric. This is called the Fubini study metric, and is precisely the metric of this variational manifold. And this can be generalized not only to calculations of the ground state, but calculations of other target wave functions, as I'm going to show you next. So the next 20 minutes or so, we're going to focus on calculating spectral functions using variational wave functions. So the first part of my talk was about representation and calculating ground states and energies. And now I want to show you how we can calculate actually a spectral function. A spectral function is something that can be actually measured experimentally. Ground state energies, or energies in general, cannot be measured. What you measure when you do an experiment is transition between energy eigenstates, and these transitions are that when a transition is allowed, what you get is a response at the energy difference between these two states. So what you measure is energy differences and not energies. And this is observed in experiments such as these. These are from neutron scattering. Neutron scattering is one such technique. It's called basically energy loss spectroscopy, in which you shine a particle to your sample. This particle bounces back, and you measure how much energy and momentum was transferred to the sample. And this allows you to basically calculate a sort of absorption spectrum, if you will, right, of energy. And these are examples in quantum magnetism. This is for square lattice. This is for 1D lattices and 1D chains, and you see how theory and experiment agree very well. And in these three cases, at the bottom, in one dimension, you can use matrix pair states, and you can get some really nice numerical results to compare to experiments. But in 2 dimensions, you know, you cannot. So the spectral function, as I told you earlier, is, you know, I'm not going to spend time on this slide, but all I want to say is that, as I told you earlier,
Adrian, let me make a question. But to calculate the spectral function, you need excited states, and you showed us how to get the ground state. So
correct. That's where I'm going next.
Okay.
Exactly.
Okay.
Very well. So indeed, so the spectral function, you know, you can derive it. You know, sometimes you're given. You know, if you read a solid state book, they tell you, okay, this is a spectral function. But where's the spectral function coming from? Well, you can do the derivation. It comes from perturbation theory, time-dependent perturbation theory, in which you study, you know, what happens when you have scattering between an incoming particle and your sample, and you end up with an expression that looks like this. Basically, it's Fermi's golden rule, where O is some operator that describes the scattering between the particle and the sample, and could be a spin operator. And here you see that you're going to get a response at all the energies omega or frequencies omega that correspond to a transition between the ground state and excited state. Now, how do we calculate it in practice? Well, I'm going to show you two methods. And I have to come clean to you. This is what we did. We basically, my expertise is in matrix product states and DMRG, and for the past 20 years, I've been using this technique to calculate spectral functions. And I realized, okay, matrix product states are variational states. We can easily calculate spectral functions with matrix product states because it's all matrix algebra. But what if we have a more general variational wave function that cannot be easily optimized? Can we still use them to calculate spectral functions? So we can basically adapt all these techniques used with matrix product states to arbitrary wave functions. And this is where basically this is what's coming next. So first, what we do is we take, if we want to calculate Green's function, and this is exact, I mean, I'm not making any approximations. So you have to calculate some Green function where, now my operator is, I call it A. I may be acting on two different sides, I and J. Basically, this operator acts on the ground state wave function. It sort of evolves in frequency with this operator, 1 minus H. This Z here is given by the energy plus frequency plus some complex broadening. And in general, for spins, this operator A is going to be the Fourier transform of a Z. So it's going to be something more complicated like this. But you see that inside this sum, what you see is exactly the same expression here and here. So we're going to focus on basically calculating this sandwich. And once we have these sandwiches, we can construct this quantity here that has momentum and frequency resolution. So if you focus now on this expression, you're going to see that we can obtain it in the following way. First, we act with A on the ground state, and we get a new vector A. And then we apply 1 minus Z minus H to this vector A to get yet another vector, now depends on Z. This is called the correction vector. And now we can obtain the Green's function as the overlap between chi and A. That's it. And this chi is obtained, I mean, I can invert these terms into this equation, and I can pass Z minus H multiplying to the left. Basically, I get the system of equations for chi, right? So this state, I know it because I know the ground state. I can get it with the variational wave function, for instance. I apply the operator to that ground state. I can do it very efficiently. But now I need to get this chi. And to get this chi, I need to solve this system of equations where, my matrix of coefficients is given by the Hamiltonian and frequency and ground state energy, etc. So this is what we need to solve. And if we are able to solve this and obtain these states, all I need to do is calculate the overlap between these two states, and I get, shown here, the spectral function, which the spectral function is in reality the imaginary part of G. All right. So again, what we need to do is solve this system of equations as shown here. And we do it again by using the Fubini study metric. Basically, we have this state, A. We know how to calculate it variationally. And what we need to do is find this state such that it approximates A as close as possible. And we do it by minimizing the distance between these states. And we get a system. We get a natural gradient descent or generalization of the natural gradient descent method to find the correction vector. And once we find the correction vector, we calculate the overlap between the two functions, and we get the Green's function. Notice that this problem, though, depends on the frequency z, right, or omega. And now we need to solve it for each value of frequency. So we need to solve it hundreds of times. So we need to run this in many processors simultaneously to obtain all the frequency range. This is a very simple example that we use as a benchmark. You know, this is for 10 sites, and for 10 sites we can do it exactly, and we can do it with an RVM very efficiently. And you see that the agreement, basically you cannot distinguish one curve from the other. So this is for different values of momentum. This is frequency, and this is the amplitude. And you see that the peaks are one on top of the other. And this is telling us that for 10 sites, an RVM is basically practically exact. And here, what we are doing is we're working in frequency, right? So we're not calculating ground states, we're calculating this correction vector. And this correction vector basically is an approximation to your excited states. So what we're seeing here also is that these restricted Boltzmann machines are pretty good at representing excited states. However, well, first, if we want to go to larger system sizes, we can do 30 compared to dynamical DMRG. And we see that basically, in reality, we need to compare this one to this one and this one to this one. The agreement is well, in this picture, you cannot see a difference, basically, right? If you look at it in color. But now, let's look at it in more detail. Let's make some cuts, some vertical cuts at different values of momentum. This is what we saw earlier, right? So we cut in momentum and we get a curve as a function of frequency. And this is what we see. So in black, we see dynamical DMRG, which is basically exact. And in color, we see vector correction in red. And you see that it performs quite poorly. The peaks at the right position, but the higher energy features are not very well described. There's a long tail. What we had to do is use some tricks that I'm not going to describe. They're very technical and they require a lot of math, but we can do some corrections to reduce the error. And you see that these corrections allow you to get closer and closer to the actual spectral function, but still, it's satisfactory, but not as good as we would like. So let's try to understand what's going on. So basically, let me just tell you in a nutshell what's going on is that it's a combination of the expressivity of the neural network when you go to larger system sizes and the difficulty of optimizing them numerically. So most likely, all these errors actually stem from poor optimization of the wave function, which is a very difficult task. So now in the next 10 minutes, maybe, how much time do I have left?
Around that. Yeah, 10 minutes.
Okay, let me wrap up then. This is going to be quick. Let me give you another way to do this approximation. So we're going to do is use Chebyshev polynomials. So Chebyshev polynomials are basically a family of polynomials, the same as Legendre polynomials, Hermite polynomials, that form an orthonormal basis according to some measure. So they are defined in the -1, 1 interval, and they are orthogonal according to this measure, and they also obey, same as the other families of polynomials that I mentioned, some nice and elegant recursion laws. So the first polynomial is just identity, the second one is x, and then all the other polynomials can be obtained as 2x tn minus t and minus 1, basically. So because they form an orthonormal basis in -1, 1, that means that we can represent any function in this interval as an expansion in terms of these Chebyshev polynomials that looks like this, right? It's basically the sum over all the Hermite polynomials, some coefficient in front of the polynomial times the polynomial. And this coefficient is basically the overlap between the polynomial and the function, and it's called the Chebyshev moment. And basically, if you know the Chebyshev moments, you can calculate any. Well, if you want to calculate expansion, you need to calculate these integrals, these Chebyshev moments, and you're done. But now we are going back to the Manybody problem. How can we apply the Chebyshev expansion? Well, we recall that the spectral function now is given as this now. I just rereading it in a different form. Now, this delta is the Dirac delta. And the Dirac delta can assume a very simple expansion in terms of Fermi polynomials. Can be written like this. And now what we have to do is find these coefficients, these Chebyshev moments mu, right? And these Chebyshev moments mu now are given by this. Is the Chebyshev polynomial of the Hamiltonian, which is between a psi and a psi on both sides. So the trick now is to calculate the following non-orthogonal Chebyshev vectors. So I'm going to define some Chebyshev vectors instead of the correction vector. The first Chebyshev vector is going to be A applied to the ground state. And the other Chebyshev vectors are going to be the Chebyshev polynomial of the Hamiltonian times T0. And the moments now are obtained basically by calculating the overlap between the Chebyshev vectors. And we can generate the Chebyshev vectors with this recursion, right? We can take advantage of the recursions obeyed by the Chebyshev polynomials, and we can get T1 as H times T0 and Tn plus 1 in terms of Tn and Tn minus 1. So it's kind of almost like, for those that are familiar with it, kind of like a Langshaw's recursion, but it's slightly different. And now what we obtain is these vectors. And one important thing about these vectors is that they are not orthogonal. The Langshaw's vectors are orthogonal, the Chebyshev vectors are not. So we so we did this. We used also the the Fubini study metrics and natural gradient descent to calculate all these vectors, and we had to optimize basically. This is a recursion. So first you have to get the ground state, then you apply A to the ground state, and then you apply H to this state, and then you apply the recursion 100 times. So you have to basically optimize 100 wave functions, and it cannot be done in parallel this time because it's a sequential process. Each Chebyshev vector depends on the previous two. But it's very straightforward and efficient, and can be done. For instance, here I'm showing you results for 32 sites. This is for momentum pi over 2, and you see how, as I increase the number of momentums, of Chebyshev moments, I mean, the result approximates better and better the spectral function, and eventually converges. And this is the final result. So this is what it looks like. So this is our result using RBMs with Chebyshev. This is using DMRG with Chebyshev, and you cannot really tell the difference, at least in this color plot. We actually did Langshaw's. So we used not only Chebyshev, but we used Langshaw's. We did the same with RBMs, and we did with DMRG, and you see that indistinguishable from one another. So here I show some cuts. So this is RBM against versus DMRG, and this is not dynamical DMRG. We use the Chebyshev moments to calculate the spectral function. So because the peaks are no longer Lorentzians, if you're used to calculating spectral functions, you know that these peaks usually are Lorentzians if you do Langshaw's, but in this case they're no Lorentzians, and you see that the agreement. I mean, it has a very smooth behavior, and the agreement is much better than the previous case with the correction vectors. And this is with Langshaw's. You also get very good agreement. And this is in 2 dimensions. So here we did 6 by 6, the 6 by 6 square lattice. We can do it exactly with the exact dimension. We did RBM. And the RBM describes very well the low energy physics, the first peak or two. but the high energy tail, you know, I guess you need more moments to either we need more moments to get the high energy features, or more expressivity in the wave functions. That's not clear, but my guess is that it's probably moments or convergence, because here clearly we have an issue with convergence. We have a double peak structure there. So finally, to wrap up, let me conclude. So we developed two new variational algorithms to calculate spectral functions of quantum many-body systems based on machine learning ideas, and the information about the wave functions is encoded in a machine. And basically, we're establishing two new formats to calculate Green's functions directly in the frequency domain using variational Monte Carlo. This can be extended to other variational forms, not only RBMs. We can use the same tricks with convolutional neural networks or any variational wave function that you want. And the main difference with the methods used with matrix pro state is that now we need to do Monte Carlo sampling, and we need to do natural gradient descent, basically something that you don't need to do with tensor networks. And again, in this case, we show that the method can be made quite accurate if we are able to control the convergence and the expressivity of the wave function, which are the main limitations. And these are basically numerical limitations or technical limitations. They're not limitations like the limitations we have with exact diagonalization, right? In exact diagonalization, we can do 6 by 6 and that's it. Here, the limitation is basically finding more efficient methods to converge and scale this to maybe to larger system sizes. It shouldn't be that difficult. So this is these are optimistic. I have an optimistic perspective on this, and I'm hoping that we can keep improving and moving towards 2 dimensions. With this, I want to thank you very much for your attention, and I welcome your questions.
Thank you, Adrian. Very nice talk. Very nice talk. Questions, anyone? We have 27 people in the audience.
There is one question, I guess, in the chat. Mark,
yeah.
Can you read it for me? I cannot see the chat.
What means the connection from A1 to H1, H2, H5 physically? What is the physical meaning of the connections?
Here. These connections?
Yeah. I think you read it as A, but it's sigma.
Right. No biggie. So I understand. So this is a mathematical construction that basically defines a classical Hamiltonian, right? This is a classical Hamiltonian, and we are hoping that this classical Hamiltonian can reproduce a probability distribution, an arbitrary probability distribution, such as the probability distribution of the coefficients of the wave function. But in a sense, it's like, I mean, probably you can think of a classical quantum correspondence here. You know, it's like you're using a classical distribution to represent the quantum mechanical distribution, but I'm not sure how accurate that analogy is. But that's it. I hope I'm answering your question.
Well, apparently he doesn't have a mic.
But basically, it's just a mathematical construction that allows you to represent relatively a broad family of probability distributions.
Ed, okay.
Go ahead.
Yeah. No, there is a background noise in your microphone, something that keeps popping up, and I don't know what it is. Yeah, that's fine.
There is one joiner.
Yeah, go ahead. Go ahead.
It's a big noise. Sorry about that. The question is maybe I'm not sure if it's a good one. Now you compare your result with something you know. How far you can go, like larger chain, using the same the machine learning machinery.
That's a good question. So the you know, for these are basically proof of concept benchmarks. They are not dual state-of-the-art calculations. We could, in principle, for chains, we could go to systems at least twice as large as this one, easily. And for square lattices, right now, as I told you, my student is working on getting the 12 by 12 to converge. But you know, in those cases, already getting the ground state is challenging. So getting when you have frustration, we have J2. When you don't have J2, you can get 12 by 12 quite accurately with several digits. But even calculating the ground state becomes challenging in 2 dimensions. So we did 6 by 6 here, but what we are working on right now is using different variational forms. As I told you earlier, but looking at convolutional neural networks that may be more suitable for 2 dimensions, and we eventually, but first we need them to work for the ground state, and that's already quite a challenge. So this is all work in progress. This is very fluid right now. You know, a lot of people are working on this, and you see papers on the archive every other day with a new trick to get them to converge better, or a new variational neural network form. But the one trick that we're using right now is we're using neural networks with Langshos. So this is something that Sorella and Federico Becca have done in the past with Jastrow wave functions, and projected with Gutzwiller wave functions. And here we're doing it with neural networks. But
okay, just trying to set up in my brain is in connection with your question at the beginning of the talk. So you use the MRG to calculate the ground state and the machine learning to calculate the Chebyshev coefficient to accept, so to speak, the excited state essentially, right?
But no, we do it 2 different ways. So we do DMRG, and it's a fully DMRG calculation. You know, we get the ground state and the spectral function using DMRG, or we do a full like Monte Carlo calculation with neural networks. We calculate the ground state using a neural network, and we calculate all the spectra using neural networks. So it's we don't mix I'm using DMRG here just to benchmark the accuracy of the results.
So thanks.
Can you quantify the concept of expressivity? Can you quantify it a priori? I understand that a posteriori you can say, well, I got close to the.
I wish we could, but what we, you know, people are looking at, for instance, is what's the entanglement structure that you can represent with variational with the different variational states. Can you represent area law, volume law, different scaling behavior with these wave functions? And that's something more on the quantum information side of things. And I would guess that's possibly the easiest way to somehow get an idea of the expressivity. for instance, we know that matrix product states are very good at representing states with the area law, but not with volume law. So that gives you an idea of, how constrained this blue bubble is inside the Hilbert space, and you can do the same with neural networks and try to figure out what kind of states you can represent accurately and what states you cannot. But yeah, that's
it. Okay.
the idea.
So let me see if there are any other questions. Anyone? Eduardo left, and thank the speaker and the very nice talk. No more questions. Edson, anything else?
I'm still trying to process.
Okay. Maybe Edson asked you that already, but that was a question I thought about. Did you get an intuition about what kind of systems this method is better adapted to from the use you made up to now? Can you tell is 1D, 2D, frustrated systems, ordered systems, critical systems? I don't know, what do you think is the better contribution of this method will be? Can you tell that already?
This clearly giving us trouble with frustrated systems in 2 dimensions, but the results we are getting are better than the MRG. So in that sense, in 2 dimensions, we can do better. But when you put frustration, things get quickly complicated because of the complicated sign structure of the wave function, right? So the wave function has a nodal structure with some coefficients are positive, some coefficients are negative, and they're in principle they can be real. For the ground state they're real. So the getting this sign structure is difficult, and we don't know whether it's a problem with the expressivity of the wave function or it's a problem with the convergence, with the optimization procedure. So there are people that are trying different things. For instance, there are people that tried using 2 neural networks, one to learn the sign structure and the other one to learn the amplitudes. And again, as I said, this is all very new and people are working on it. So at the moment, every evidence I can give you is only empirical by experience. I cannot really give you any rigorous result.
Okay. So no more question, I guess. So let's speaker again. Very nice talk. So very soon it's going to be posted to our YouTube channel, so you guys can watch it again. And I